Hello. In this session, we will talk about the representations of a function as a power series. So first of all, let's say that being able to represent a function as a polynomial with infinitely many terms is a powerful tool. Yes? And we may think why we even want to do this. I list a couple of applications. That means this is quite useful. For instance, if we would like to integrate a function and we do not know the direct antiderivatives, the elementary antiderivatives, it will be helpful to have a power series, like a polynomial representation. Then polynomial involves elementary formulas. Also, similar ideas, solving differential equations. Yeah? We may not know some antiderivatives, some steps, and if we rewrite a complex function as a polynomial with infinitely many terms, it will be easier. Approximating a function by polynomial, again, that's we can see everything has the same idea, the same fundamentals, because polynomials are the easiest function. They involve only the basic arithmetic. That's we can do this. Scientists, computer scientists, they will actually do this to simplify their work. Okay, and now we definitely have to ask the question, when can we represent a function? Or maybe what type of function? That's we will talk about this in finishing the whole topic. But today we will focus on a certain function that actually we may get the power series representation for. And we will just look at the geometric series. We know this. We will try to manipulate just algebraically, or possibly also trying to take the derivatives or the integrals. Okay, that's me. Let's see. Geometric series, that's what I mean. We did talk about this. That means this is the geometric formula, powerful tool for us at the moment. A power series x to the power of n starting from 0 to infinity. If x is, because x is like a common ratio, that means if x is between -1 and 1, yes, the interval of convergence, if we like this way, is between -1 and 1, and radius is 1. And actually the center is 0. We know all of these parameters. Okay? And then if x is from this interval, we know that this is power series is convergent, and we may use the sum. We remember, yes, we remember the formula of the sum of the geometric series 1, I mean a, as a first term, 1 minus the common ratio. Since the first term is 1, we have 1 over quantity 1 minus x. And now, actually thinking backwards, having a function 1 over quantity 1 minus x, this is a rational function. And if we will get the question, please get the power series representation, we know that this is this power series, and just this quantity, because we can see x and x, just this quantity is raised to the power of n, starting with 0. That means the power series representation for the function 1 over quantity 1 minus x is summation x to the power of n, x to the power of 0, x to the power of 1, x to the power of 2, x to the power of 3, and so on. And we may instead, that's what I was referring about the applications, instead of taking this rational function, we may take the polynomial with infinitely many terms, or we may use truncated version, like a shorter version, and for instance have the linear approximation. If we remember, like, find the linearization for the function center at 0, we will just get 1 plus x. You may try. Or we also talk about the quadratic approximation. For let's take this function at 0, we will get 1 plus x squared. Now we know that we may even approximate more accurately. We can have the third degree, fourth degree, fifth degree. Okay? But this is the point. And we will use this as a tool for more complex function, if we can, of course, because we always need more tools. Okay, that means please remember 1 over 1 minus x is represented by the power series x to the power of n. And this is the expanded form. And of course, we can only talk about this if x is between -1 and 1. Okay, let's start. Exercise number 1. Express the following function as a sum of a power series and find the interval of convergence. Okay, and we can see perfect function, rational function. That means probably we may use this geometric tool, 1 minus quantity x. It's represented by the power series x to the power of n. And that x is less than 1. Okay, that's our tool. Okay, so now let's see. 1, we have like the templates, 1 over 1 plus x squared. I mean, I can definitely see that this is 1. The only thing is we subtracting that common ratio, if I can name this way. As we have addition, we will have subtraction of a negative number. Okay, perfect. So now we may rewrite this as a power series, summation from 0 to infinity, and just this quantity, negative x squared, is raised to the power of n. We can see that x is raised to the power of n. Okay, that means that's almost everything. Let's just split. It's negative 1 to the power of n and x to the power of 2n. We remember we have to just have the variable. Okay, that means this is the power series representation for this function. Finding the interval of convergence, we know that this is called the common ratio. This means the common ratio must be less than 1. Absolute value of negative numbers are positive numbers. We may take the square root of both sides. I mean, theoretically is the same. Yes. And practically. Okay, beautiful. This is the power series representation for the given function 1 over 1 plus x squared. Exercise number 2. Okay, find the power series representation centered at 0 for this function. 1 over quantity 2 plus x. Perfect, that means the same thing. We have 1, we do have 2. That means we will factor out 2 because we need to see 1 plus and then x over 2. Okay, that's when we have 1/2, 1 over quantity 1, and addition, we don't like addition, we will get the subtraction of negative number. Perfect. And now we can see 1 over quantity 1 minus that common ratio. That's we are ready to rewrite this as a power series, negative x over 2 to the power of n. That means this is the power series representation for the given function. Let's clean it a little bit. Let's rearrange. Negative 1 is raised to the power of n, x is raised to the power of n, and 2 in the denominator is raised to the power of n. We will also move that 1/2 behind the sigma. This means I can remove this one. And this is 2 to the power of n and 2 to the power of 1. We may combine this. This means the final answer is summation from 0 to infinity, negative 1 to the n, x to the power of n, and 2 to the power of n plus 1. Now looks beautiful. I mean, this is power series representation. This question is not asking for the interval of convergence, but let's just get it. This quantity must be less than 1. We may ignore negative. We may multiply by 2. Okay, that means an interval of convergence is between -2 and +2. Yeah, centered at 0. Perfect. Okay, exercise number 3. Find the power series representation centered at 0 for the function f of x equals to x cubed times 1, 2 plus x. And we may notice this is just what we did. I separate the x cubed. That means this is exercise number 2. Let's copy this. Or you may pause the video and you may do it again on your own, okay, independently. But I will just copy. This was summation from 0 to infinity, alternation, x to the power of n actually. Yes, do we remember? We will check in a minute. And 2 to the power of n plus 1. Let's check. Yes. Okay. But as I said, you may try to do this exercise again. Okay. That means that's almost everything. But we know that we will combine these variables because that's not, yes, that's not good. We will simply move it behind the sigma. Okay. That's mean now what we have. We do have summation from 0 to infinity, -1 to the n, and then denominator stays, but x will be raised to the power n plus 3, n plus 3. We may remove this one. Okay, this is power series representation, and also copying from exercise number 2, we know that the interval of convergence is between -2 and 2. You may pause the video and try to get the interval. Okay, exercise number 4. Oh, okay, find the power series representation, but centered at 5. And we know whatever quantity is subtracted from x, from the variable, that's always the center. Yes, if we remember the first session about power series. So we know what we can do. Oh, let's use the red color. I hope you working along with me. Yes, and you writing down everything because nothing is most powerful like a pencil and the paper, or pen and the paper, and writing down. Okay, that's what we have. We have 1 plus, and I would like to see this in my sigma notation, x minus 5, because this indicates, yes, from basic formula, the general formula for the power series, that this is centered at 5. Actually, I can maybe write this down. We remember coefficient and then x minus a to the power of n. That means this is the center. Of the interval. Yes, of the interval of convergence. That's mean that's the center. That's what we do have. Okay, but since I subtracted 5, I will add 5. That means now our function looks like 1 plus 5, 6, and I will keep this one together. Okay, we don't like 6. Okay, that means I will factor out 1, 6. This will be 1, and this will become x minus 5 over 6. Okay, I believe we are ready. 1, 6 can stay. Oh, one more thing. 1 minus 1 over quantity 1 minus, because we have plus. And subtracting negative, x minus, oh, well, x minus 5 over 6, but this is negative. Oh, my writing is not clear. 5 and okay. I mean, this is that common ratio that we will place in the sigma. Okay, let me write here. F of x equals to 1/6 times, and the power series representation, it's this quantity to the power of n, negative x minus 5 over 6. And we can see x minus 5, I am taking this to the formula, and this will show that this is center. Okay, let's try. 1, let's try to simplify. Okay, -1 to the n, as always, alternation, x minus 5 to the power of n, and 6 to the power of n. Everything is taken to the power of n. That 1/6, I will move behind the sigma, because it's not affected, it doesn't include but it will be power series representation, will be summation from 0 to infinity, -1 to the n, x minus 5 to the power of n, and then 6 to the power of n plus 1. Okay, I mean, this is the power series representation. And interval, we are not asked, but let's see, this is the moment that I'm using this. That's mean that common ratio, negative x minus 5 over 6 must be less than 1. We may ignore negative because absolute value of negative is positive, and we may multiply by 6. Okay, and then x minus 5, oh, we found must be between -6 and +6. Yeah, that's how we're solving inequalities with absolute value. Adding 5, it will be between -1 and 11. And if I draw this, x, -1 and 11, I believe 5 is in the middle. And we're not testing the endpoints because this is based on the endpoints are not part. We will get divergence. Okay, that's mean, yeah, this is 6 units this way, 6 units this way. That's mean radius is 6. Yeah, let me actually write this, but 6 and the same way, 6. Okay, that's we have radius, we have center, and we have an interval. But we can see the similar question to exercise number 2, but centered at 5. That's it. Please remember that magic, subtracting and adding. Okay, exercise number 5. Oh, wow. Okay, that's mean now we see the squared. 1 over quantity 1 minus x squared. Of course, the first thing is we cannot really square, yeah, this will be not the same. 1 minus x, because we like this, squared. I mean, this is still the same, but we cannot say, oh, this. Okay, I will erase this, but this power series representation for this rational function is x to the power of n. We okay with this, but I cannot say that they are equal because this is expanded form. It's like 1 plus x squared plus x cubed. And when I grab everything and squared, that's, yeah, we cannot do, yes, we cannot do this. Because we know, like, let's maybe say this, a plus b squared is not a squared plus b squared. We also have to add 2ab, then it's equal to. That's definitely, that's not a good way. Yes, we will not do this way. Let me erase. You may pause the video and look at the, we have to figure out a different way because algebraically this will be incorrect. Okay. We may think that this is the derivative because if we take, for instance, a function g, like this one, because we like this function, so we still want to use it. And if I will find the derivative, let's see what is the derivative. It's 1 minus x to the power of -1. That means we will have negative 1 minus x to the -2 and times derivative of the inner function negative. That means derivative of the function g is negative times negative is positive, and 1 minus x squared, wow, is actually identical function. That's we may say that this is derivative of g of x, and this is g of x. We know because it looks similar, and of course this is our tool, powerful tool. So I can rewrite this, that this is the derivative of 1 minus x. Okay. Let me make this a little bit smaller. Okay, this is the derivative. Okay, that means now what we can do, we may differentiate that power series because we know that this is the power series representation, x to the power of n for this function, 1 over 1 minus x. And now, yes, now it's okay. That we can see we're not really squaring, we're differentiating. And we may do the expanded form, or we may actually do just the formula. Okay, let me expand this. Oh, let me expand without the x to the power of 0, x to the power of 1, x to the power of 2, x to the power of 3, and so on. And now, taking the derivative, let's maybe do this. We may use the sigma notation right away because I also want my students to know. That means we will have a summation, and x to the power of n derivative is just n x to the power of n minus 1. The only thing is we have to be careful with this index. Since the first term after the expansion, we can see here, is a constant, derivative of the constant is 0. That's when we're losing the first term. Instead of starting from 0, we will start from 1. That means this is the final answer. And let's see derivative of, if we're looking at the expanded form, derivative of 1 is 0, derivative of x is 1, derivative of x squared is 2x, 3x squared, 4x cubed, and so on. That we can see, n x to the n minus 1. And we're losing, yes, we're losing the first. That means this is basically the first term, this is the second term, and makes sense. Okay, that means we remember the differentiation. That means this is quite nice question, but we use the derivatives. Okay, radius of convergence, of course, is 1. Interval and radius, center at 0, because we're not subtracting anything from x. One more thing I was gonna say, sometimes we like actually to rewrite this and start from 0. Yeah, that we will re-index. The first term must be like this one, 1, meaning that n must be 1. If I put 0, I have to add 1. Yes, and then n minus 1, 1 minus 1, 0. We can see x to the power of 0. Then I need 0, I can just have n, because n is 0. That means this expanded form will be identical like this one. That's important. Make sure that you know how to reindex. Okay, good question. And always pay attention to this index. Okay, let's keep moving because we have more. Exercise number 6. Oh, this one is easy because you may notice we will just use it's x times 1, 1 minus x to the power of 2. And this is exercise number 5. I will really recommend that you will pause the video and try to do it again on your own. Okay, x, and I will just copy. Let's start from 1. Okay, because I mean, we can do 1, let's just put 1, because that was just the derivative n x to the n minus 1. And when we move n, I mean that x, if I move that x behind the sigma, this is 1, then we will have n minus 1 plus 1 n. Okay, that means this function is this one. Or if we like to reindex, let me cancel this one. We will start from 0. That means n, the coefficient n for the first term, actually I can even expand this. It will be 1 x to the power of 1, 2 x to the power of 2, 3 x to the power of 3, and so on. Now we have to have the same. Yeah? That means 1 x to the power of 1. Then I need n plus 1, because n will be 0. 0 plus 1 is 1, and n plus 1. Okay, and then we will have exactly the same. That's how you can always double check. Okay, and interval is the same. Okay, Okay, that's good, yes, good practice of the power series representations of a certain function. Okay, exercise number 7. Oh, wow. I see another quantity squared. Yeah, that means we will use the derivative. Let's see. We have a function 8x, 1 plus quantity, 1 plus quantity, quantity 1 plus x squared squared. It's what function we like. We like definitely 1 plus x squared, because we can get a power series representation easily. But let's check the connection. And you probably know why I am doing this, because I like this denominator. That's where this comes from. Okay, let's find what is the derivative. That means derivative of this will be 1 plus x squared to the negative 1. That will be negative 1 plus x squared to the negative 2 times 2x. Okay, let's rewrite. Negative 2x over quantity 1 plus x squared squared. That's we can see almost the same. Almost the same. And then we can say that if I just need, in order to get 8x, I have to multiply by negative 4. That's in function f of x is defined as a negative 4 times this, correct? Yeah, then, oh, I don't actually need the extra parentheses. Oh, no, we need the, okay. That means I can say that this is negative 4 times g prime of x. Yes, that's that, because that's g prime of x. And so we like this function. Okay, so now I can say it's negative 4 times derivative of the function g. Because we will not use just the rational function. We will actually use the power series representation for this one. And that's me, let's see, negative 4, and we will differentiate. Function g of x, the power series representation, is summation, and we adding, that means we will subtract a negative x squared to the power of n. You may try again to pause the video and get this power series representation. Shall I maybe do this? I will just try, because we did, I think the first question was like this. Power series representation, because it's addition, subtraction of a negative x squared to the power of n. Okay, please pause the video and you may try to get this. This was, I think it was exercise number 1. Okay, that's me. Now let's just make a nice, let's clean it everything before taking the derivative. Negative 1 to the n and x to the power of 2n. Okay, because we will only differentiate the variable. We will not differentiate the constant. And let's think, just because we don't even have to expand, we may expand, but when we expand this, the first term is taken to the power of 0 is 1, x to the power, that means it is a constant. We will lose this. That means let's just use, actually, let's expand this. The first term is 1. Then the second term is negative. To the n is 1, then this will be 2. Then n is 2, this will be 4. Then n is 1, 2, 3, this will be negative 6, and so on. That we can see the first term is constant. Taking the derivative of the constant, 0, we're losing the first term. That's we will have negative, and then 0 minus 2x plus 4x cubed minus 6x to the power of 5, and so on. You may do right away. That's we will have negative 4, starting from 1, because we're losing the first term. And now, we remember, copy the constant, negative 1 to the n, and just differentiating this, the variable, just differentiating x to the power of 2n. It will be 2n x to the power of 2n minus 1. And we can see 2, 4, 6, and then even numbers 1, 3, 5. And this is, but we still have to change that negative 4. Oh, I need one extra line. Okay, let me use maybe blue color, and this will be the final answer. Power series representation. That means I will copy starting from 1. Yes, I'm just copying this. And now we will have 2n x to the power of 2n minus 1, negative 1 to the n. But negative 4 can be rewrite as a negative 1 times 4. Correct? And that negative 1 is taken to the power of 1. That means I can combine with this one. I can add plus 1. Okay, let me write a little bit nicer. Negative 1 n plus 1, that's we don't need this. And 4 times 2 is 8. That means I can put 8. And this is the combination, nice final form of the power series representation for this function. Yeah, this is supposed to be written at the bottom, but it is here. Okay, this is the final answer. Really nice question, really nice question. Okay, let's keep working because I have plenty of exercise and I really recommend that you may pause the video, you may watch later, you may practice later, but I will recommend solving all of these exercises. I have 15 of those. Okay, exercise number 8. I can leave it this one for you because it's identical to exercise number 7. I mean the similar concept using the function g, and I will add the solution later. Okay, check the notes, check the lecture notes. And then exercise number 9, let's do it together. Find the power series representation for the function natural log 1 minus x and its radius of convergence. Okay, that's we definitely see that this function doesn't look like rational function. Yes. Okay, but since this is the only tool for us today, we have to figure out. We know the rational function, the power series representation for these rational functions, and that's the only tool. But we also know that we may differentiate or integrate. We just did the derivative. That's we may realize that integral of this, still small correction. Integral of this is actually integral of function that we like. We can see 1 over 1 minus x dx equals to this function, but actually negative, correct? But it's okay, we can have it negative 1 because the u substitution and so on. So that's what we like, this function, okay, integral, and this rational function, the integrand, can be rewrite as a power series x to the power of n, starting from 0, ending at infinity. Okay, and we may integrate this. That means integral, again, we can 1 plus x squared plus x cubed, and so on. That's when we may integrate term by term. We don't need this. We may just integrate the sigma. That's me. Let's do it this way. Integral of 1, and we even gaining a constant. Integral of 1 is x. Integral of x is x squared over 2. X squared, integral, x cubed over 3, integral of x cubed, and so on. And we even gaining a constant. I will add at the beginning because then we will keep the order. Okay, that means this is actually the power series. We still have that negative. That means each term will be negative. Or I can use the sigma notation right away, gaining a constant minus and the summation, we're not losing anything, any terms, we even gaining. That means we start still from 0, and then integral of this variable, integral of x to the power of n. X to the power of n plus 1, we can see x to the power of n plus 1 all over n plus 1. I mean, this is the solution. Okay, this is the solution. Natural log of 1 minus x is defined as a constant minus the summation, the power series representation for the natural log, x to the power of n plus 1 over n plus 1. Really nice, really nice. We use the integration. And when was the moment? Again, this one. That means this is a power series, radius or interval. Radius is 1. Because the center is 0. Yeah. Okay, really nice. And have the solution, you can check up, you can also check this one. And let's do this one, okay? Maybe as a last one. Because I said that I have a little bit more, but you can practice. But let's do this one. This one is also interesting. Inverse tangent, or I can say arctangent. Then we know the domain. Okay, arctangent of x, that's the same thing. Yeah? I know that sometimes inverse tangent, arctangent. Okay, the same thing. Doesn't look like a rational function. We cannot use directly our geometric power series representation for the geometric series, but we may notice that integral of the rational function like this actually is equal to arctangent of x. So that's what we will do. We will integrate that power series. And again, exercise number 1, power series representation for 1 over 1 plus x squared is negative x squared to the power of n. Okay, let's rewrite negative 1 to the power of n and x squared to the power of n. And in order to integrate, we will gain the constant. We're not losing any term. That means I keep 0. I copy the constant, and we just integrating x to the power of 2n. X to the power of 2n plus 1 over 2n plus 1. Yeah, that's really nice. And actually, when x equals to 0, the center, the constant is 0. Yeah, because we can see arctangent of 0 is 0. This will be 0. Constant is 0. And we may, because you may probably see sometimes the formula, actually. For arctangent of x, yeah, without the constant. That means power series representation is negative 1 to the n alternation x to the power of 2n plus 1 over 2n plus 1. Okay, that's quite important formula. We will need this. We need all of them, but this one is quite helpful. Arctangent of x can be rewrite as a polynomial. Let's maybe expand. We can see just odd exponent, 2n plus 1, and the same 2n plus 1 in the denominator. When n is 0, it's x to the power of 1. And then when n is 1, is x cubed over 3. When n is 2, positive, x to the power of 5 over 5, and then x to the power of 7 over 7, and so on. Okay, that's arctangent. Of course, when x is 0, constant is 0. And I also have a one just for your information, for nice fact. Oh, that's actually, yeah. Actually, this example, number 10, yes, the power series for arctangent or inverse tangent is called Gregory series, and it's actually it's also called, it's a beautiful result, and it's known as a Leibniz formula for pi. Actually, this one, because what we can do. Okay, first of all, this formula is called Gregory series. I'm just because I was actually more excited about this. But we can see when x is 1, when x is 1, arctangent of 1, which is pi over 4, we may approximate pi over 4 like this one. Yeah, because we remember was x and then was x cubed over 3 and was x to the power of 5 over 5 and then minus x to the power of 7 over 7 and so on. And then if x is 1, we have 1/3, 1/5, 1/7. That means this is the approximation. If we multiply everything by 4, we will get the formula for pi. Yeah, that's another way to approximate the pi. That means it's called Leibniz formula for pi. But in general, let me just finalize this. Yeah, this formula is called Gregory series, and it's one of the Scottish mathematicians who actually work on this discovery. Yeah? Okay, that's me. Let's finish. Let me put one more time. Arc tangent of x. The power series representation is the sigma summation power series from 0 to infinity, -1 to the n is alternation, and then x to the power of 2n plus 1 all over 2n plus 1. And we can see just the odd exponents, odd powers. Okay, enjoy the power series representation and work with all of these examples. You can check. I can maybe show you. You have to do this exercise. You have to do this exercise. Oh, this one. Okay. And this one and this one. I have 15 of those. Actually, before I finish this one, I wanted actually to do this one with my students. I think I was planning to do this one because this one is another way. Okay, let's actually finish with this. You may, of course, pause the video and but let's finalize with this. For x's from -1 to 1, find the sum of the power series. That's we have the sum. I mean, we do have power series representation, and sum means the corresponding function. That means it's this. We can see this question asked the other way. That's what we can see. We definitely see n minus 1. We may think, let's kind of like reverse this. -1 to the n x to the n minus 1. I will say that this looks like, actually looks like the derivative. Because when I have x to the power of n, derivative of this is n x to the n minus 1. That means this is derivative. We will copy this and 0 because we're losing the first term. Okay, and now let's combine. Let's go backwards. Derivative. Yeah, I'm like reversing the process that I did for a couple of exercises before. Now let's combine. Actually, -1 and x is raised to the power of n. And this is the power series representation for the function 1 minus -x. Correct? And now we will just find the derivative of 1 plus x. And derivative of this is -1 plus x squared. And derivative of the inner function is 1. That means this is the final answer. You may maybe take a couple of extra seconds longer to find the derivative. But we can see this question, actually, it's really nice. I forgot about this question. This question asks you the same thing, but backwards. Having the power series representation, we have to figure out a function. Okay, now I can finish. Thank you and enjoy the power series representation.